Okay, so we will start. Okay, so we will continue with chapter 5, part number 2. Okay, currently we are seeing about fluid mechanics and also the fundamental terms that we will be using for our analysis. So there are various terms that we need to understand. Okay, in order for us to know how to use, how to calculate, and how to define. Okay, in your exam. Okay, so yesterday we have seen some terms, and I already explained to you. So I will upload the video later so that you can listen back. Uh, and today we will cover another important term under this fluid mechanics, which is called viscosity. So viscosity is something that we deal with every day. So almost every day, so in our vehicle, in our daily life, and viscosity plays a very important role in whatever things that we are doing, especially in engineering. Okay, we will see what viscosity about. Okay, so if you we recall viscosity expressing the magnitude of internal friction in a fluid as measured by the force per unit area resisting uniform flow. Okay, so viscosity is something that acting in the opposite direction of the flow. Okay, so if the flow is going to the left, so viscosity will be on the right, so it will be opposing. Okay, so because of the opposing force, so it will resist a uniform flow. Okay, and all the fluid that is traveling, so maybe it can be in a pipe, can be in a duct, but if it's traveling from one point to another point, it is subjected to internal frictions. Okay, so yesterday we have seen this formula, so how to calculate viscosity. So shear stress divided by velocity gradient du dy. Okay, then we can calculate the viscosity. Okay, viscosity is caused by the cohesive force between the molecule in liquid and by the molecular collisions in gases. Okay, so the fluid that we are dealing, so there are two types. One is liquid. So in liquid, viscosity is determined by the cohesive force between molecules. So you have a water molecule here, you have a water molecule here. So this is a cohesion. So it is holding each other. Okay, so the more closer, more stronger it is holding each other, so the viscosity will be higher. Okay, that is for liquid. Okay, for gas it will be different because all this molecule will be distributed. So it won't be at one point, it will be moving in random. So the molecular collision, so of course when the molecules are moving in random motion, so it will be colliding with the other molecules. Okay, the more it collide, the more viscous the gas will be. So there are two things that differentiate liquid as and the gas. Okay, so we need to understand. Okay, so viscosity of gas is based on molecular collision, and viscosity of liquid is based on cohesive forces between molecules. Okay, so that's the important part that we need to understand. Okay, so viscosity varies greatly with temperature. So we know temperature plays a very important role. So we have covered this yesterday. So usually temperature and slightly pressure will be affecting viscosity. Okay, so I have given you the example. So why we need to change the engine oil frequently, maybe 3 months or 6 months, because it will be subjected to environmental temperatures, the temperature in the car. So after some time, the cohesive force between the molecule will be not strong anymore. So you need to replace it with a new oil. So in order to ensure that the efficiency of the machine or the engine will be good. Okay, so the viscosity of liquid decreases with temperature. Okay, so liquid So as long the temperature is going up, the viscosity will be lower. So why lower? Because the molecules will, instead of holding each other, so it will be trying to escape. So when it try to escape, the cohesive force will be lesser. So the viscosity will be lesser. Okay, in liquid, the molecules possess more energy and high temperature. So as I say, the molecule will get more energy for it to escape, and they can oppose the large cohesive intermolecular forces more strongly. As a result, the energized liquid molecules can move more freely. Okay, so instead of holding each other, it will try to escape. Okay, the viscosity of gases increases with temperature. Okay, so it's opposite. Gas is always opposite of liquid. So if the temperature increases, so the viscosity will increase. So why it will increase? Because when the temperature is increasing, the molecule will move more faster. So it will move more faster, so it will collide more. So when the collision happens more, viscosity will increase. Okay, so in a gas, the intermolecular forces are negligible, and the gas molecule at high temperature move randomly at higher velocity. This result in more molecular collisions per unit volume per unit time, and therefore is greater resistance to the flow. So, uh, so this is the graph. So comparing liquid and also gas. So this is viscosity over temperature. So as the temperature increases, uh, the viscosity of liquid will decrease. Okay, will decrease, but gas will have a different opposite reaction. So as the temperature increases, the viscosity of the gas increases. So these are some of the things that we need to understand. Okay, so you maybe need to pay some attention to this part, because I think one part of the final exam questions will be covering in one of this topic that we will be covered today. So please pay more attention. Okay, so on the calculation side, the viscosity of gases is expressed as a function of temperature by the Sutherland correlation. Sorry. So Sutherland correlation. So this is based on the United States standard atmosphere. Okay. So that's another formula to calculate the viscosity of a gas. Okay. So using this formula, so AT to power of half. So divide by 1 plus B over T. Okay, so what is T? So T is the absolute temperature in Kelvin, and A and B are the experimentally determined constants. Okay, so usually if there's any possible questions from this part, so they will give all these values for you to calculate. Okay, the air at atmospheric condition, the value of this constant are equals to 1.458 times 10 to the power of negative 6, and B 110.4 Kelvin. Okay, so these are the important information that similarly can be given for your question. But for air at atmospheric condition, so this will be the constant. Okay, so we see for the liquid. For liquids, the viscosity is approximated as so for liquid we will use this formula. So A 10 to power of B over T minus C. Okay, so what is T? T similar is absolute temperature in Kelvin. A, B, C are the experimentally determined constants. So which will be given. Okay, for water, so water is a part of a liquid. For water, the value of these constants are as shown. These are like fixed for water. So different liquid will have different values. Okay, so usually if there's a questions here, so they will give all these values for you to substitute and find the answer. So result in less than 2.5% error. So this is for the water. So it will usually will give plus minus 2.5 percentage. Okay, within, because it's an experimentally determined constant. Okay, so you can see this table. So dynamic viscosity of some fluid at 1 atmospheric pressure and 20 degrees Celsius. Okay, so you can see glycerate. So we have engine oil. So I think if you usually service your car, so you bring for service, so you will see at the bottle, so it will be written 10W, 10W30, 30, 30, 50, so 20W50. So all that are different viscosities. So different viscosities of engine oil. Okay, so mostly the engines can take, uh, they will give the best recommendation, but usually it can take almost a similar, because you see, so here 0. 0.1, 0.17, so it's not varying too much, like the other type. So if let's say there's a leakage in your engine oil tank, so maybe instead of you're taking a lighter viscosity engine oil, so maybe the mechanics can suggest you to take a thicker, more viscous uh, engine oil. Okay, so it will prevent the additional leakage. So viscosity plays a very important role. So then we have like mercury, ethyl alcohol, water, okay, blood, gasoline, ammonia, air, hydrogen. So all these are some of the values that already calculated. Okay, so you can see this figure. So from this figure we can see, so this is the absolute viscosity over temperature. So the top part are mostly on the liquid side. So you can see is going down. It's going down because as the temperature increases, the viscosity will start to decrease. Okay, but for gas, so it will be, yeah, opposite. As the temperature increases, uh, the value of viscosity also will increase. Okay, so consider a fluid layer of thickness within a small gap between two concentric cylinders. The gap between the cylinders can be modeled as two parallel flat plate separated by fluid. Okay, so this is a lab experiment to determine the viscosity. Okay, let's say you have a fluid. So let's say you have oil. So you want to calculate the viscosity. So what we will do? So you will have this kind of cylinders. Okay, so this is a top view. Okay, so you'll have a cylinder. So this is the outer cylinder, which will be stationary, and inside you'll have another cylinder, so which will be moving. It's attached to the motor. So it's a similar concept like blender in the house. So where you there will be a motor down there to rotate. Okay, so this part, the inside part will rotate, and the outside part will be stationary. Okay, so in between these two cylinders, so you left gap. So at this gap, you pour whatever fluid that you want to measure. Okay, so the liquid. So let's say you want to measure the viscosity of water. So fill this part with water. Okay, so when you on the motor, so the inner part will start to rotate, and it will start to create a velocity profile. Okay, so yesterday we have seen why the velocity profile is like that, because this is a stationary side, and this is the moving side. And here you will have a no slip condition. So because of the no slip condition, the end up the profile will be like this. Okay, so some of the formulas that you can use, you will use to calculate. The first one is torque of inner cylinder. So torque T equals to Fr. So that's the first formula that you need to know. F is the force, and R is the diameter. It's sorry, radius. So radius. So radius of the inner cylinder. Okay, so you just need to substitute here to in order to find the top. Okay, so if you put it in a straight line, so it will be like this. So you'll have a non-moving plate, and you'll have a moving plate. So in between you have fluid. Okay, so it will create a velocity profile. So when the top plate is moving with some force, so velocity will be changing. Okay, so the second formula that we will use the shear force. So shear force F equals to tau A. Okay, and it can be changed depends on if let's say this question comes in your exam. So you need to see whether they give the rate of deformation du dy, or they give a value of velocity and also the thickness. So usually for this case, they will give this part, the behind part. Okay, so you you can calculate. So you calculate based on this mu VOL. Okay, so as it is moving, so it will create a tangential velocity. So tangential velocity's formula is V equals to omega r. So omega is the angular velocity, and r is the radius. Okay, so the relationship between the angular velocity, okay, angular velocity is when, because this inner cylinder is moving. It's moving, it will create a angular velocity. So the angular velocity omega equals to 2 pi. So n dot. So n dot is number of revolution per second. So like here you can see they give in revolution per minute RPM. So you need to change to RPS. Okay, RPS. So revolution per second. Okay, then you can substitute to find the angular velocity. Okay, the wetted surface area of inner cylinder can be given as, so area equals to 2 pi RL. So this is the area for cylinder. Okay, so you can find. Okay, so if you see, we have seen a few uh, formulas. Okay, like torque, shear force, tangential velocity, angular velocity, and area. So all these can be used to calculate the viscosity. So, okay, so you can see here. So how we can substitute into this formula. So Fr, so force is mu VOL A. Okay, so don't forget the A behind, times with R. Okay, so you expand it, so you get like this. Then you just substitute with all these formulas. So V equals to omega R. Okay, so A is 2 pi RL is substitute. Then you try to simplify it until you get this formula. Okay, so at the end, you can just use this formula to calculate the top. Then you can calculate the other part, especially the viscosity. Okay, so we move to another part. So earlier we have covered on the viscosity. So now we will see another application or event that happened in fluid mechanics. Okay, we call it. There are two events. Okay, one is surface tension, and another one is capillary effect. Okay, so there are two things that we need to understand. Okay, we will see what is surface tension first. Okay, so you can see these photos. Okay, so normally if you see you go to a river or you go to a pond, so you can see the small insect. So they will be standing on top of the water. Okay, on top of water. So they will be standing as if like it's like a normal ground. So what actually enables them to be like that? So we will see that. And at times you put a leaf on the water, so the leaf will be floating. Okay, so it's not because it's light or what. It can be because of its light, but there is something else that helping in order for it to float. So that is what we call as a surface tension. Okay, so liquid droplet behave like a small balloon filled with a liquid, and the surface of the liquid acts as a stretch elastic membrane under tension. Okay, so surface of a liquid. So we always understand that it is like a elastic membrane. So it can stretch, or it can shrink. So depends on the situation. The pulling force that caused this tension acts parallel to the surface and is due to the attractive force between the molecules of the fluid. Okay, so you will see later. I will show you another picture. Uh, so the top part of water or any fluid, it will form like a layer. Okay, it's a layer on the surface. So it's happening because of the attractive force between the molecule of the liquid at the surface. So because we know if you have a water, so water molecule will be everywhere in the water. So it can be in the inner side of the water, or it can be at the surface. So when the molecules at the surface, so it try to hold each other. So earlier we saw how the cohesive force, so the molecule will be holding each other. So similarly, here it will try to hold each other, okay, and it will create uh, like a layer, okay. So which will help all these small insect, so which light in weight, so it can just just like stand on top of the water. Okay, the magnitude of this force per unit length is called surface tension or coefficient of surface tension. Okay, so this is the symbol, and is usually expressed in the unit Newton per meter. Okay, so the effect is also called the surface energy per unit area and is expected in the equivalent unit of meter. Okay, so you can see. So to visualize how surface tension arises, considering two liquid molecules, one at the surface and one deeply within the liquid body. So you have a container, you have a liquid. So you pour inside. So the molecules can be either at the surface part, or it can be also at the bottom part, a bottom part of the liquid. Okay, so bottom part we can see the molecule is experiencing force from all the angles. So all the angle. But the top part we can see the molecule will be only active within the liquid. So on top, so no force, no force is released. Okay, so what it will do? So it will uh, create force to the sides. Okay, so for the right and left, so you have other molecules inside. So this molecule will is like you are pulling their end. So you are holding their end tightly. So it will form like a layer on top. The attractive force applied on the interior molecules by the surrounding molecule balance each other because of symmetry. Okay, but the attractive force acting on the surface molecule are not symmetric, and the attractive force applied by the gas molecules above are usually very small. Okay, so it won't be like too strong force. It will be just like either negligible or very small. So there is a net attractive force acting on the molecule at the surface of the liquid, which tend to pull the molecule on the surface towards the interior of the liquid. So the force is balanced by the repulsive forces from the molecules before the surface that are trying to compress. Okay, so the force is balanced. Okay, the force is balanced by the repulsive force. So consider a liquid film. Okay, so you can have a frame like this. Okay, so you suspend. So this is a U-shaped wire frame. So you have one side is the movable side. Okay, the liquid film tend to pull the movable wire inward in order to minimize its surface area. So you can see, so you have this pipe. So initially it was here, but as the attractive force of the molecule in the film activates the surface tension, so it will start to move from this side to this side because it will try to minimize its surface area. Because if you minimize the surface area, then you can have more gas to be stored. So both sides of the film are surfaces exposed to air, and thus the length along which the surface tension act in this case is 2b. Okay, so 2b. Then the force balance on the movable wire gas. So this is for this application only. Okay, then the force balance on the movable wire give force F equals to 2b surface tension times surface tension. Okay, the surface tension can be expressed as, so this is the formula to calculate the surface tension, F over 2b. So you can see here in this table, some surface tension for some of the fluid at 1 atmospheric pressure and 20 degrees Celsius. You can see water, okay, 0.076, 20 degrees Celsius, 0.073, 100, 0.053, 300, 0.014. Okay, so uh, usually liquid, as we know, uh, the coercive force will be decreasing when it will decrease. So it will decrease because like how we saw earlier. So the higher the temperature, the viscosity will become lower. But for gas, it will be opposite. Okay, so droplet and air bubbles are caused by this surface tension. Okay, so a lot of factors will be influencing, like gravity. Surface tension is one of the natural phenomena that uh, we can experience. Okay, a curved interface indicates a pressure difference, pressure jump across the interface with pressure being higher on the concave side. Okay, so you have convex and also concave side. Okay, so this will be covered in the next few slides. So the excess pressure, so delta P above atmospheric pressure can be determined by considering a free body diagram of half the droplet or bubble. So let's say you want to do analysis on this. So you'll try to draw the free body diagram, so like shown here, so that you can see in 3D or 2D. Usually will be 3D, so that you can see how the force are distributed. So what are the values? So you can just include it here. Noting that surface tension acts along the circumstances and the pressure acts on the area. The surface tension, it is not affecting the pressure, that is acting on that particular area, but it will be more on covering the circumference. Okay, so horizontal forces balance for the droplet or air bubble. Okay, so these are some of the formulas to calculate. So all these questions we will see either at the end of this chapter. So if we have time, or we will see in. Sorry, hold on. Okay. So this is on the horizontal forces. Okay, for the droplet or air bubble. Okay, so this particularly for the normal air bubble or the droplet of water, and this can be for the soap bubble. So it can have a difference. So you can have a difference in terms of the formula. So we will see some of the questions. So maybe at the end of this chapter, okay, if we have time, or as I say yesterday, so we will be covering at the end of our semester during the exam clinic. So you can have some tutorial questions there for you to prepare for your final exam. Okay, so that's on the surface tension. Okay, so as I say, these are some of the natural. Because if you've seen the midterm question, so you can see the type of question that will be asked. So usually, so you need to answer a principle based on a real life experience. So real life situation, the real life phenomena. So whatever we are learning in thermofluid, so we need to link with the surrounding and also the environment. Okay, and whatever things that we are experiencing daily. So surface tension and capillary effect are something that happen naturally. So which is a part of our life. So it will be good for you to understand so that you can give it as an example during your exam. Okay, so we'll move to the last part of our slide, okay, for this chapter. Okay, so which is the capillary effect. So earlier we have seen about the surface tension. So now is what is capillary effect? So capillary effect is a raise or fall of a liquid in a small diameter tube inserted into the liquid. So maybe when you are small, you always will try to play this. So you take a pail of water and you try to put a cup inverted, try to press inside, and you can see the water try will be rising inside the cup. So you get excited. So maybe I am not sure about you all. So during our time, we don't have all these handphones. So we are trying to come up with all sort of things in order to enjoy the life. So maybe if you never tried this before, so later after the class, you just go to your bathroom, take the pail of water, so try to put a cup inverted. So you can see the water level will be rising. Okay, and we also, I'm not sure whether we are having this anymore, but those time we always use a kerosene lamp. Okay, so you put a kerosene inside, and so you have a thread which will be used to light up the room. Okay, so all these are using the capillary effect. So the narrow tube or confined flow channel are called the capillaries. So whichever things that you are putting and where the water is moving upward or downward, so we call it as a channel of confined flow channel called capillaries. So we call it as a capillary. So the curve-free surface of a liquid in the capillary tube is called the meniscus. So if you see the water, because of this capillary effect, so you'll have a meniscus. So meniscus, it can be either downward, so like U, or it can be upward, like N. So it can be either two. So it can be like U. So U will be like this. So at the side it will be higher, and it will go lower like U, or it can be like N. Okay, so facing downward. So what's the difference? The strength of the capillary effect is quantified by the contract or wetting angle. So if you see, um, when you are putting in a container or the channel, or we call it as capillaries. Let's say you put the water. So water we know is a wetting fluid. Wetting fluid means uh, the meniscus will be like you. So that is what we call as a wetting fluid. So then you can calculate the angle. So you just need to see uh, the end part. Then you just connect it straight. Then you take the angle from the surface down. Okay, then you can get this angle. And similarly for mercury, it will be non-wetting fluid, so it will be like N, so it will be downward. So you just need to connect it, connect it further, and you take from the surface of the container. So don't take from down. Okay, so you need to take from up to down. So you can see the angle is bigger. So here the angle is smaller. Okay, so a liquid is said to wet the surface when the angle is less than 90. So like this, the angle is less than 90. So we know that is a wetting fluid. And here we can see is more than 90. Okay, so maybe under 30, under 40 degrees. So we know that it is not a wet. It will not wet the surface. The water molecules are more strongly attracted to the glass molecule than they are to other water molecules, and thus water tends to rise along the glass surface. So maybe the question can come: why actually this thing happened? So the water level initially is at this level. Then when you put a tube or a container inside, why the water is going up? Okay, so we can ask this question. So they give the answer here. Uh, so the water molecules are more strongly attracted to the glass molecule than they are to the other water molecules. So we know inside this water we will have the water molecules. So water molecules, and here the glass will have its own molecule. So what it will do, it strongly when it strongly attract to the glass molecule, because usually the opposite sign it will attract the opposite sign, or a bit something that is further, so it will give more attraction. Okay, so in this case, the molecule glass at the glass and the molecule of water will have more stronger bond compared with the molecule of water to other molecules. So what it will do, so when we are putting uh, the the capillary inside the water, so it will create a force, and the force will pull this water upward. Okay, so the force will be helping, and will form meniscus, uh, wetting or non-wetting. Okay, so for mercury, so it will be the opposite of water, because this is non-wetting, so it will go down. Please hold on. Okay, so the magnitude of the capillary rise in a circular tube can be determined from the force balance on a cylindrical liquid column of height h in the tube. So you can see, so you have a liquid, so you put a capillary, and you can see the liquid enters and it rise, and you have a meniscus. Okay, meniscus. So you have a meniscus, the angle, so you can calculate. And here we have h. H is from the normal surface, how much it rose. So the height is h. Then you have weight, and also the diameter of the tube. So the bottom of the liquid column is at the same level as the free surface of the reservoir, and thus the pressure, there must be atmospheric pressure. So usually, so since it is exposed to the atmospheric pressure, so it will be the same at the surface level. The balance, the atmospheric pressure acting on the top surface of the liquid column, and thus these two effects uh, effects cancel each other. Okay, so balance of atmospheric pressure. So you have the top surface here and also here. So it will be negligible. So negligible because it will be almost the same. Okay, so the weight of the liquid column. So this is the column, liquid column, and you have W as a weight, and you have radius 2r. So you put all the information here. So weight W equals to mg. So we know how to calculate the mass times gravity. So this is actually density times volume times gravity. Okay, then you just replace V with um, this is for the cylinder pi r square h. So area of the cylinder times width, the I. Okay, then G is gravity. So equating the vertical components, so we know. So we want to find what is W. So W is actually so you can see there's a angle here. Um, okay, so this part, so we can have horizontal and also vertical component. Okay, so since we want to take from top, so we will take these two. So we will take the cos component. Okay, so weight is actually same as surface force. Okay, surface force. So you can just replace it. Okay, so weight equals to surface force, then the height. So you rearrange this, rearrange, you cancel, then at the end you will get this formula, which can be used directly to calculate the height of uh, the increase. Okay, so we came to yes, please. Any question? Muhammad Alif, what? Any question? Muhammad Alif, what? Okay, so I just mute him. Okay, so we have come to the end of chapter 5. So I hope you can get some picture on how. So this is just a fundamental concept of what we will be going to study in chapter 6 onwards. So related to fluid. So fluid is divided into two. It will be static fluid and also dynamic fluid. So static will be something like lake in maybe in the house. We have certain parts, maybe in a basin or pail. So all that will be static, and we will also have dynamic, which will be moving like river, ocean. So we will be calculating. So the calculation and the concept behind the calculations and will be a bit different. Okay, so I hope if can try to listen back to the video recording and try to come up with your own understanding, okay, before we enter to chapter 6 and 7 and onwards. Okay, so Any questions? Any questions? Okay, so I will share the attendance list. So wait, I will stop the recording.